Welcome back. In this video, we shall talk about ohm meters. In our last video, we talked about voltmeters and ammeters. So, this is the time for ohm meters. So, as you can expect, ohm meters will be used for measuring resistance, and we will use say a simple PMMC or maybe some other type of meters to make this ohm meter. Okay. So, the idea is very simple. The idea is to use Ohm's law. Okay. So, suppose I have a resistance, call it R x. X stands for unknown. So, R x is an unknown resistance. So, what I can do? I can connect this resistance in series with a battery with known EMF and then a meter, maybe an ammeter. Okay. So, this can be an ammeter, any type of ammeter you like, and this E is known, R x is unknown. Now, according to Ohm's law, the current that will flow through this circuit, that means through the ohm meter, this current I is given by E by R x. Now, I is observed. That means, by looking at the pointer position of this ammeter, we can find the value of I. E is already known. So, R x can be found as E by I. So, this will be the value of R x. Okay. So, this is the simple scheme of an ohm meter. Okay. Now, that is the idea. Now, let us talk about this circuit in more detail. Let us consider various aspects of this circuit. Okay. So, first thing we will discuss is how would the scale of this meter look like once it is marked in terms of resistance or ohms. Okay. So, the scale of this meter so say this is an ammeter. So, that means the left side will indicate low value of current. So, maybe I write this as 0 ampere, and maybe this is some high value of current, maybe just call it 1 ampere. So, this is the behavior of this meter as an ammeter. Okay. So, this side should be low current, this side should indicate some higher value of current. Now, when we mark this scale in terms of the unknown resistance, okay, because we want to measure resistance with this circuit. So, let me erase this and let me put the value of resistances. Now, when R x is infinite, okay, if R x is infinite, that means R x is open. So, then no current flows in this circuit. So, I will be 0. So, I will be 0 when R x is infinite. So, this side, that means current equal to 0, can be marked as resistance equal to infinite. So, R is equal to infinite ohm. This side will be R equal to infinite ohm, and this side So as I go from the left to the right, the current value is increasing, which means the resistance is definitely decreasing. Okay. So this side will have a lower value of R. Okay, Rx. Okay, lower, this is lower value of Rx and this is a higher value of Rx. So this is how the scale of this meter should look like. Okay, so this side should have higher value of Rx and this is actually infinite. Okay, because that means open circuit, Rx is open. That means we remove Rx from here. So we can remove it like this. So then this point will indicate Rx equal to infinite. Okay. Now what should be the value at the extreme right? So so we may desire, we would like, it is desirable that the extreme right of this meter this is desirable. I mean, this is also logical. I mean, if I make a meter, it is convenient to have one side indicating 0 value of the quantity that that means the resistance that we are measuring. So this is desirable. Okay. So remember that this is a desirable condition of this meter. Okay. This is I mean, if you may choose not to maintain this condition because of some other reason you may have, but in general we would like to have this side indicating Rx equal to 0. Okay. So this side should be Rx equal to 0. In bracket I write desirable. Okay. Now so this side is infinite resistance, this side is 0 resistance, and all the other values will be from here to here. So Rx increases from right to left. So this is, so let me write like this: Rx increases from right to left. Unlike voltmeters and ammeters, this ohm meter will have this opposite characteristic. And nowadays this is not very common, the analog multimeters, but if you have seen any analog multimeter in your lab, so analog multimeter means which has a pointer and you can use it as voltmeter or ohm meter or ammeter, then you will see that the scale for voltage and current has 0 on the left side and higher value on the right side, but the resistance scale is opposite, 0 on this right side and higher value on the left side. Okay. So this is how a ohm meter scales look like. Now next thing, okay, so next question is, so consider the center point. Okay, say this is the center point on the scale. Okay. So what will be the value of Rx for which the pointer will be here at the center? Okay. So the question is, for what value of Rx the pointer or the indicator will be at the center of the scale. Okay. So, to answer this question, we will assume that the right side, the extreme right side indicates R x equal to 0. Okay. Suppose I have made this circuit, that means I have chosen the value of, say, everything, this EMF, the different parameters of this ammeter, such that the right side, the extreme right side indicates R x equal to 0, which is a desirable condition. So, let us say we have this condition, this desirable condition fulfilled. Okay. If so, then what will be the value of the resistance for which the pointer will be at the center? Okay. So, let me draw this circuit once again. With a bit more detail. So, this is the EMF E known. So, this battery can have some internal resistance, maybe R I. So, we are putting more details in this diagram now. Then here I have the meter, okay, and say the internal resistance of this meter. So, this is an ammeter, and the meter resistance call it R meter. Okay. So, which can be the coil resistance, and if it is an ammeter, it can have some shunt resistance. So, the total combination of all the resistances, that means between these 2 points here and here, is R meter. Okay. Now, the unknown resistance R x will be connected between these 2 terminals. So, this is R x, okay. And now, let us call R internal equal to total internal resistance of the circuit, total internal resistance of the circuit. Okay. So, which means in this diagram this is equal to R I plus R meter, and if I have anything else, I mean also including conductor resistance, that may be negligible, but and if I have anything else in series, so let me just put any other resistance which I may have or may not have depending on the requirement. So, if I put any other resistance in this circuit, call it R 1, okay. So, R 1. So, all this together is called the total internal resistance of this circuit. Okay. Now, this is our internal. Now, if R x is equal to 0, then the current that will flow I through this meter, that or the meter reading, okay. So, this will be equal to E by R internal, okay. And for other values of R x, then I is equal to E divided by R internal plus R x, because R x and R internal, they are in series. So, R internal is all these resistances and R x is here. So, they are in series. So, if I add them, I get the total circuit resistance, and if I divide E with the total resistance, I get the meter reading current I. Okay. Okay. Now, observe when R x is equal to R internal, then I is equal to E divided by 2 times R internal. Okay, because I have R internal and Rx is also equal to R internal. So, this becomes 2 times R internal. So, this is the current when the resistance Rx is equal to R internal. Okay. Now, let me denote this as I0, this one, this particular current. So, this current is the current when Rx is equal to 0. So, this is the current I0 which is for Rx equal to 0. And this is also same as, I can write, this is also same as IFSD of the meter, full scale current of this meter. Why? Because we have assumed that the Rx equal to 0 corresponds to the extreme right side, extreme right position of the pointer. Okay. So, when that means when Rx equal to 0, the pointer goes to the extreme right. That means when Rx equal to 0, the full scale deflection current flows through this meter. Okay. So, this I can also write as IFSD. If so, now from here when Rx is equal to R internal, then I can write this I is equal to I0 by 2 from this equation, because I0 is E by R internal and this is E by 2 R internal. So, this is I0 by 2 and this is also same as IFSD by 2, because IFSD is I0. Okay. So, that means when Rx is equal to R internal, the current that will flow through the meter is half of the full scale deflection current, which means the pointer deflection will be equal to the 50% of the full scale, 50% of full scale. That means the pointer will be here at the center. Okay. So, if I choose Rx equal to the total same as the total internal resistance, then under that situation the pointer will be here at the center. Okay. So, you can also okay. So, the conclusion, so let me just write a conclusion saying that if the Rx equal to 0 corresponds to the full scale deflection current IFSD, that means or the pointer movement to the extreme right or pointer position is equal to extreme right. Okay. Then, so this is if, and then Rx equal to R internal will correspond to full half of the full FSD current or half scale deflection. That means the pointer will be at the center. Okay. Now, let us take an example. A small numerical example. Say R internal is equal to 1 kilo ohm. Okay. So, this is basically you know this R internal is Ri battery resistance plus meter resistance plus R1 etc. everything. Okay. So, say this is equal to 1 kilo. Now, and assume this condition that Rx equal to 0 correspond to IFSD full scale deflection or full scale deflection of the pointer. Okay. Full scale deflection of pointer. Now, what we want to mark the or calibrate the different positions on the scale. Okay. Now, we know that Rx equal to 0 corresponds to the full scale deflection current. So, here we can write 0 ohm. This side we will write infinite ohm, Rx actually open circuited, okay, that means no current flows, and the center point here we will write it as R internal. Okay. R internal is 1 kilo ohm, because when Rx will be equal to 1 kilo ohm, then half of the full scale deflection current will flow and the pointer will be here. So, this point is 1 kilo ohm position. Okay. Now, consider say this position, say here, which is like 3/4 from the right. So, this position is 3/4 from the right, or you can say 1/4 from the left. Okay. So, that means so you write it as IFSD divided by 4. Okay. So, here if the pointer is here, that means full scale deflection current flows. If pointer is here, no current flows. If the pointer is here at the center, that means half of the full scale deflection current flows. If it is here, that means 1/4 of the full scale deflection current flows. Now, what will be the value of the resistance that I should put here on the scale? So, this is the question, okay, and let us find out the answer. Okay. So, we know the current is IFSD 5/4. Okay. So, if the pointer is here, then the current that is flowing is equal to IFSD by 4. Okay. And this current is nothing but E divided by R internal plus Rx. Okay. R internal plus Rx, this is equal to IFSD by 4. Now, for what value of Rx this is true? Okay. So, let us solve it, and we also know that IFSD is equal to E by R internal. Okay. Because plus you can write plus 0, because Rx is equal to 0 means full scale deflection current. Now, using this equation we can write here, in place of IFSD we write E divided by R internal, okay, and this 4, this should be equal to E divided by R internal plus Rx. From this we can write, so this E you can cancel. So, then we can write 4 times R internal is equal to R internal plus Rx, which will mean I am doing a step jump, then Rx will be 4 R internal minus R internal, this will be 3 R internal. So, this point therefore, I can write as 3 times R internal means 3 kilo ohm. So this is basically R internal, this is 3 R internal. And what will be this position, say 3/4 of FSD, say this position which is IFSD multiplied by 3/4. Okay. So what will be this value of resistance? So let us find that out. Okay. So this is for position. So this calculation was for position A. Now Now for position B, let us do the similar calculation once again. It will also be our practice. So for this position, I is equal to 3/4 of full scale deflection current, and this is same as E divided by R internal plus Rx, and IFSD we can write from this equation as 3/4 of E divided by R internal, same as E by R internal plus Rx. Let us cancel E from both sides, this will imply. So let us cross multiply 3 with this. Okay. So we will have 3 R internal plus 3 Rx. Okay. So and on this side 4 R internal with some small step jump. Let me write it. 3 Rx is equal to 4 R internal minus 3 R internal. So which will be R internal, implying Rx is equal to 1/3 of R internal, and when R internal is 1 kilo ohm, then this value will be 1/3 kilo ohm. So let us put the value. So this is 1/3 kilo ohm, same as R internal by 3 in general. So this is position B. Okay. So this is the position B, this is position A. Okay. So that is how you can mark all other positions on this scale. And now you observe that the scale is non-uniform, non-linear. So scale is non-uniform. Okay. So from 0 to 1/3 of kilo ohm, so this is like 333 ohm. This region is here. Then here I have 1/3 kilo ohm to 3 kilo ohm. Here I have everything from 3 kilo ohm to infinite. Okay. So now next question we will ask is this. So let me copy this diagram. Okay. So now let us ask another question. Which region is good to use, in a sense that I mean, for what value of the Rx in this meter we can measure it with better accuracy, better precision. Okay, say now okay, so note when say Rx is equal to say 30 kilo ohm, and another situation Rx is equal to say 31 kilo ohm. These two conditions, okay, so this two values of Rx will be very close to each other on this scale, will be very close to each other on this scale. Okay, say this is 3 kilo ohm, maybe 30 kilo ohm will be somewhere here, and 31 kilo ohm will be very close to it, and therefore it's very difficult to read the difference between these two, okay, because the pointer will be so close for Rx equal to 30 and 31, it's very difficult to distinguish between these two values. And you see, all high values of Rx, they are in a very small region. Within this 25% of the scale, we have everything from 3 kilo ohm to infinite. And then say for example, now if I have 1 mega ohm and 2 mega ohm, those two will also be very close, and we cannot distinguish easily between those two positions. Okay, so it's very difficult to read resistance values which are very high value. Okay, so it is difficult to distinguish, or let's say it is difficult to read read any high value of resistance with say high precision. Okay. Similarly, so this is true for high value of resistance. So this is say note 1. Now similarly, say another note, note 2. Okay, consider low value of resistance. Okay, consider very low value of resistance. Say consider Rx equal to, say this is, so this point is around 300 ohm. So let's consider something like Rx equal to say 30 ohm, and so what will happen? The pointer will be somewhere here, almost close to 0. Okay, so here also, now if I make say a small error in reading the pointer position, say I make an error of, due to say parallax error, I make an error of say maybe 1 degree, and this 1 degree will correspond to a high relative error. Okay, say because say this position, say Rx is Rx equal to 330 ohm is say here at 10 degree. So assume Rx equal to 30 degree is situated at 10 degree from right, from right side, and then if I make an error of say 1 degree while reading or noting the value of the pointer, then this will lead to so this is like 1 degree out of 10 degrees. So, this will lead to 10% error in 10% relative error or percentage error, you can say 10% error in measured resistance, okay, and 1 degree error I can say make due to parallax error. So, once again the conclusion is low value of resistance is difficult to measure. And finally, say if Rx is close to R internal, so in this case this is equal to 1 kilo ohm, then you see the pointer is quite far from the extreme right. Okay. So, maybe this angle is almost 90 degree. Okay. So, then this position is almost 90 degree, and even if I make 1 degree error, so 1 out of 90 is almost like 1%. Okay. So, if Rx is equal to R internal, the pointer will be close to the center and say this means 90 degree, approximately say this is 90 degree from the right. Then if I make 1 degree error, this will lead to a percentage error of 1 over 90, approximately how much it will be. I mean, this is approximately 1%, much less than this. And also, okay, so this is 1 kilo ohm. Now, consider the value of 1 kilo ohm and 2 kilo ohm. Also, considering Rx equal to 1 kilo ohm and Rx equal to 2 kilo ohm, the gap between them is good enough. Okay. So, 1 kilo ohm is here, maybe 2 kilo ohm will be somewhere here between 1 and 3. So, we will have a sufficient gap between 1 and 2 compared to say 30 and 31, which are very close to each other. So, this gap between them is good enough compared to 30 kilo ohm and 31 kilo ohm. Okay. So, it is difficult to distinguish 30 and 31 kilo ohm, but it is easy to distinguish 1 and 2 kilo ohm. Okay. So, the central part is most ideal region, or is the best region where the precision of our measurement will be most, the accuracy will be most. So, the conclusion is, so the central part of the scale will have best precision or accuracy. Okay. Right now, we haven't defined these terms formally yet, we will do that later. So, let me write, we will have least error. Okay. We will have, so this is the important observation. Now, next what we should do, therefore, depending on the value of the resistance that we want to measure, we should alter the markings of this scale. Okay. So, if we want to measure say 10 kilo ohm resistance or a resistance which is close to 10 kilo ohm, then we should somehow change the circuit so that 10 kilo ohm comes at the center. Okay. So this will be the focus of our next video. So let's continue with ohm meter in our next video. Thank you. Thanks for watching.